ahead, Mrinal.
All right, so hello everyone. So today I'll be presenting my paper, not my paper, I wish. Today I'll be presenting this paper that was published in ICML 2023 by authors Ziken He. The name of the paper is Contrast with Reconstruct. So it's a constructive 3D representation learning that is guided by your generative pre-training. I know the name sounds very complex, but I swear it's very, very easy. So before we even delve into the exact, what exactly it says, I will first cover few preliminaries, like what self-supervision is, and then I'll come up to what contrastive learning is and generative learning is, so that everyone is like on board. And if you have any questions, please do let me know, and you can stop me in between. So self-supervision is like, okay, so even though we have like a lot of data available, right, in the world, in order for us to train any image for machine learning or deep learning purpose, we need to annotate it, and that's a very expensive and expensive and time-taking process. So that's the reason you need techniques such that you can build your deep learning model and also have all your databases available. So that's where self-supervision comes into picture. So that's without you even requiring any expensive annotation or learning feature representation, you can use the data that you already have, and then you can try to supervise that data and learn from it, and then do whatever downstream tasks that you want to do. The self-supervision mainly consists of two parts. The first part is the generative learning, and the second part is contrastive learning. For generative learning, I guess all of us must have heard about GANs, Generative Adversarial Network, and of course diffusion is also a part of it now. So that is a part of self-supervision algorithm, and contrastive learning has a lot of algorithms, like I guess Infomax is one of them, and NCE is also one of them. So like contrastive learning, I wanted to build more upon what contrastive learning is here. So it's basically it's a very similar approach where you will be grouping similar images closer, and you will be removing, or you will be pushing the dissimilar images far away from each other. So your distribution will only have those images which are similar to each other, and it will not have those images which are dissimilar, just like how the image is showing. So you can see the negative. So okay, those images which are very similar to each other, they will be called the positive samples, and those which are dissimilar will be called the negative samples. Now, in order for you to check like how you can see like two images are similar or dissimilar, you have some few metrics which are called similarity metrics. So in the context of natural language processing, you must have heard about something called cosine similarity, where you can see how similar two vectors or two embeddings are by using cosine similarity. But in the case of contrastive learning, you have info NCE as well as Infomax. So this is a loss function which defines what contrastive learning does. So you have the negative expectation of log of exponential, like the exponential of your positive samples divided by the positive samples plus. So if I have just one sample which is a positive sample, I will take n-1 samples as my negative sample. So that's how it works. And then I will calculate how similar they are. If you guys have any question in that, please do let me know.
Is that just entropy?
What? The E?
Yeah.
No, that's expectation. It's a mathematical formula. It's a mathematical expression where you take the average of your distribution. So
no, but that's what it means. It's negative sum of logs, right?
Yeah.
Yeah. Oh, yeah. Yeah, that's it. Sorry. Yeah. So that's contrastive learning. So now let's come up to the actual paper that they say. So even though we have like a lot of images and a lot of images, a lot of text, and so mainly these algorithms are being worked on 2D images or text. But for 3D representation, it's a very difficult approach, because first of all, you do not have a lot of images or a lot of data sets in itself right now, and it's very difficult for you to pre-process it and for you to model from that particular data set as well. That's why it makes sense for you to take into consideration an algorithm that has something specific to self-supervision. So, but with this approach, there are two problems. First, anyway, since we are going to take the approach of self-supervision that consists of contrastive learning and generative learning, you have issue with each of these parts. So with contrastive learning, you should know like your model will be very data hungry. That will of course suffer with overfitting, and then your generative model is like it has the issue of data filling that shows inferior data scaling capacity compared to contrastive learning. So you won't be able to see like how scalable your like images. But for example, if I take an algorithm like diffusion model or GANs, I can scale that image from a low resolution image to a high resolution image, but that cannot be done in contrastive learning, I guess. So what recon or contrast with reconstruct does, it actually combines both of these algorithms together, both of these approaches together, while removing each of the problems which are associated to these issues. These issues meaning the issues related to contrastive learning and generative learning. So this is what we'll be checking out. So
that question. So the problem with contrastive learning is it can't scale.
The contrastive learning, it can scale, but it just suffers from representation issues. Like it's very data hungry. You cannot do it with just few images.
Okay.
But the problem with generative image that it actually shows that it can scale, but it's not that much better than contrastive learning.
No, but I can comment to that because the wording, I'm having trouble with the wording as well, what is there. But I was kind of stuck on the representation over fitting. And actually, Alex is not on call, but in his recent work that we're submitting soon. And other people also have noticed, like Likun and others, they talk about contrastive learning or self-supervised learning is helpful for transfer. Like you train on one data set and you transfer to another, but it turns out more and more experiments showing that because of this representation overfitting, it doesn't overfit because you don't train it on a signal, on classification or something, you train it just to represent the data. So it learns to perfectly represent the specific data set that it was trained on, and then you try it on a very different, like domain shift or something, and it fails. So that's what representation overfitting, even though you're only building representations by playing with this data, but it's kind of learning that's like to represent this data set specifically. You need very large data set in order to be able to.
And it's actually more common in 2D images, but like 3D is like
Everywhere it turns out, yeah. Even harder, fewer samples.
So the problem with these parts is like, as I was mentioning, so representation overfitting is what is associated with the contrastive one. So as I mentioned here, like for example, you can actually, contrastive learning it fails to bring generalization in your pre-trained data. But with the issue with generative model is like you have an issue with data filling because you're not able to scale it up properly, while generative model only provides like a very little improvement. It also shows that contrastive models can easily find shortcuts with trivial representations that, like for example, that overfits the limited data, right? And the generative model are like less data hungry, that learns decent initialization with very few data. So these are like few problems that they mentioned in their paper as well. And just to compare the concept of this, so in the left side you have the contrastive model, in the right side you have the middle one, B is generative, and the third part is what they are actually proposing with. So in the contrastive modeling, you have one input, you transform it into some transformation, and then you generate two views from that. So what they are trying to show you is like they're trying to show you in the case of a knowledge distillation. So knowledge distillation basically tells you if you have a student model and if you have a teacher model, then how will they actually interact with each other in order to give you an output. So in the left side, the teacher encoder and the student encoder, basically, if you have a global token, you will perform, you will have a contrastive loss, and then you can check like which images are similar and which images are dissimilar. While for the generative mass modeling, you will have the same thing, you will have one input, you will be transforming into two views, and then you will be performing the reconstruction loss in order to find, in order to check if your teacher is actually learning, if your student is actually learning from what your teacher already has. So just like what you have in the generative model and as well as a descriptive model in GANs. Now, what they're trying to do in the recon is they are having the same input, but they have, okay, so it's kind of, they have the same input, but now they're trying to transform it into two transformations. First is the M transformation and second is the T transformation. And now they want, so in this case, the local student encoder and the global student decoder actually represents the, so the local part is actually the local part is actually associated to the generative models, and the global part is actually associated to the contrastive learning. And they guide your generative model in order to create better representation for the contrastive learning. And they do it, but like I'll explain like exactly how they do it. But what they also mentioned is like because they're unifying these two methods by learning from multi-teacher, where the generative local student is also a teacher that guides the contrastive global student. And like afterwards, I will actually show you like how good the results are by combining these two paradigms. So let's go to the next part where, in the previous part I explained like what contrastive learning is and what the generative learning is, and the recon is basically a mixture of contrastive as well as the generative model. So we will go through each of the parts. Like first we'll go through the contrastive modeling, like what exactly they do, and then we'll go towards the generative, and then we'll see like how they actually combine them. So in this case, they basically use us to encoder decoder style architecture, where your the overall representation learning is basically formulated as a distillation with both teacher as well as the student model. So the key insight with contrastive learning is invariance learning. Invariance learning, as I mentioned, so it's like this: you have all your images. So in this paper they basically mentioned one thing as well. There's a very popular paper that was published by Google. It's called SimCLR. Now, the problem with SimCLR was a very basic problem with SimCLR was that since it's being trained on the single image, and they're also trying, so it's being trained on the single image. They're taking the single image, and then from that single image, they are basically transforming that image into two views, and then they are trying to do the reconstruction loss. But what if, let's say, if my image is an airplane, but what if in this case, what if my airplane is a part of that negative sample? Then that just defies the whole purpose of a contrastive learning, because now that airplane with another view is basically the same as our airplane in the positive view. So that was a problem with SimCLR paper that they are also trying to rectify. Did you get like what I'm trying to say with the SimCLR part? So what they're trying to do is they actually, because of which they're trying, so the invariance learning is something that I just explained you right now. So they're just taking like one image, and from that one image they're trying to generate views, and from that view they will be doing some downstream tasks. So the optimization target for this, basically what it does is you have the loss of reconstruction, loss for reconstruction, and then you have the two views which I mentioned in the previous image. So you have X, which has been transformed, which is T of I, and then you will be giving it to some function which has the parameter theta. So theta parameter will be associated to your student. Theta parameter will be associated with your student, and phi parameter will be associated to your teacher. So I'll just explain here. So the teacher parameter, I mixed it. So the teacher parameter phi can be same as the theta parameter, but without the stop gradient. And so since they are also trying to do the multimodality, you can see that the phi and theta can be different for different modalities in this case. The T of the, I'm not sure if it's just T or, yeah, okay, T of I and T of J are basically the two transformation of your input data. So what I meant by transformation is like you can do like a data augmentation, you can rotate it, you can scale it, you can do whatever with the image. You do the transformation of the input data that belongs to your transformation pair, and then you can reconstruct, you can construct the positive as well as the negative pairs, invariance targets, yes. And then your L will be the loss, L will be the distance function, which is defined on the metric C. So the distance function is what is something that you can use, like whatever you want to use. You can either use Infomax. They tried with Infomax, they tried with L2 distance as well as the Info NCE. Info NCE, yes. So this is for the contrastive part. Now let's go to the generative modeling part in this case. So similarly, what they did with the contrastive learning, they have one image which is X, which is with the same distribution D, and you will be so you have D, and then you will be defining a student network which is f of theta of student with the parameters of theta, and f of phi, which is basically the teacher network with the parameters of phi. And then you will be generating the mask modeling for this model. So you have L rect in this case is basically the distance function that is defined by the sum space D. And in this case, for a generative modeling, you will have something called, like, let's say the reconstruction loss that you have already for that, for the transformed embedding, which is Z of I and Z of J. So do you have any questions till here? So now, since you have already calculated all your reconstruction loss as well as the contrastive loss, you will be doing the ensembling of these two parts by doing the representation distillation. So your student is trained with ensemble distillation is known to be like more informative and like instructive. That encourages your student network to learn the embeddings and disentangle any knowledge representation. So what that means is like you will only be learning those parts that you want from that you want from your teacher model, and you can just disregard any any false information that is going to alter your output from that from the model. So this is the overall architecture of this model. So as you can see, it's kind of complicated, but I'll try to simplify it as best as I can. So you have multiple inputs in this case. So first of all, since we are trying to do the 3D representation using this this architecture, you will see that you will be taking the 3D point cloud inputs. 3D point cloud inputs, and for that specific 3D point specific 3D point input, you will be taking a 2D image as well as the text input of that. So this text input is basically coming from a pre-trained text encoder. In this case, they have taken a very famous model which is called CLIP, which is a very powerful model as well. And for the 2D image part, they have taken like a simple image, simple model, which is the VIT. Visual transformer, I guess. So by combining these two parts, you're basically converting that into an embedding, and then coming back to the generative part, you are generating the mask from the 3D point cloud inputs and pointing it into the local 3D cloud encoder. And from there, you are doing the cross attention to the locally guided decoder, which is a generative model. From that generative model, whatever output that you're getting, you are basically checking that with the output of your contrastive modeling. So when you see that, you can actually check whatever you're getting is, so you can use whatever output that you're getting for any downstream purpose. I'll explain like what other downstream purpose that they use it for. Now, but due to limited 3D data, right, the contrastive model can easily learn any trivial representation as shortcuts, and that's the main thing in this. And this could lead to like noisy training signals, which can harm any generative image. Because of which they use, you can see the stop gradient there. So because of which they use the stop gradient so that they can, so that your gradients do not actually mess up with the already generated image, which which are going to be used for any other downstream purpose. So,
but then how they are connected if you're not, how do you back propagate to this decoder?
So the backpropagation for the decoder, it's actually, so they leave the locally guided 3D point decoder as it is. I mean, okay, yeah. So what happens is whenever you're doing the backpropagation, you don't want your gradients to flow from the contrastive model towards the generative model. That's the reason they use the.
So you train the generative model by
You
reconstruction error, a separate reconstruction error, and you train the rest by contrastive. So like that's where the gradients
Yeah, that's
are for the contrastive model, like at the top there.
Yeah.
And at the bottom, 3D point cloud inputs, that's where reconstruction error that you check. How do you
how do you
even train the decoder? I don't
The
see how you
decoder?
train the decoder, yeah.
Oh, so the thing is like, so the left side one is basically
No, reconstruction loss. So that's
Oh,
what I'm saying, yeah, okay.
yeah, you have
Reconstruction loss is on the left there, so you are just training decoder by reconstruction loss, and it's kind of independently trained, but it participates.
It participates in the identifier of.
Like there is no reconstruction loss anywhere else, it's only.
Yeah, it's only on the decoder side.
See, oh wait, but reconstruction loss does flow back into the contrastive. It's the contrastive loss.
Contrastive flow that cannot go back, because then it will mess up with the representation.
I don't know why, but okay. Why
Yeah,
one
no,
messes
they
up, the
mentioned-
other one doesn't, but okay.
They mentioned that because it could lead to like noisy training signals, and like, if you flow through it.
Why reconstruction loss doesn't do the same?
That they have mentioned as well. I'll let you know.
Okay.
Yeah. So yeah, so basically, in this case, what they're also doing, they're conducting a dense mask modeling with the encoder. So that is there on your left hand side. So which produces the features to guide the global contrastive learning through the sparse query based decoder, which is your right hand side, the orangish kind of part, and then they are okay, and then you have like a cross attention algorithm, which basically goes from your generative model towards your contrastive model, and then you will be creating the representation for your downstream task. So that is what happens in architecture, and this is kind of a. So I'll come up like why this architecture is so complex in this case, but we'll check that.
Yeah, it feels like a large MLP would do that altogether.
So these are the downstream tasks which happens if like after these after you try to train from this model. So first of all, what you're trying to do is they are doing the 3D real world object recognition. So for which they used a scan object NN dataset. So they mentioned that this is a very challenging 3D dataset, which I don't know, like I never worked with it, so I'm not really sure. So they actually came up with a good result using these three downstream tasks. In the third one, which you can see like 3D zero shot recognition, which they're doing which is similar to CLIP, where they actually claim that they are getting better results using this recon block rather than just using the CLIP model. But so it's actually kind of, when I check the code, it's actually kind of shady, because I'm not able to figure out like how they're actually doing the zero shot recognition. But one thing which is really good in this case is it's not just like for single modality, but they're also doing for different modalities as well. So they also tried different contrastive metrics, as I mentioned before. Oh, sorry, L1. Yeah, L2. So they tried it with info NCE, L2 distance, the smooth L1 metric, as well as the cosine similarity. Surprisingly, I thought like info NCE would perform better, but in this case, smooth L1 is much better than. like,
What is L1?
It's just,
L1.
Yeah,
Yeah.
element smooth.
Well, but that's not the point of L1. Yeah.
yeah, I don't know, I think they just mean that.
There is no formula? Like
No, they didn't give any formula in that.
Smooth L1 loss, yes, by torch,
It's just like normal,
mean square error.
it's-
No. No. It's just mentioned there. Square term if the absolute element-wise error below beta. Oh, okay. So
That's a fun-
it's your
just the curve.
yeah, like it curves at the end. Yeah. Okay.
Yeah, so that was surprising to me because I thought like for any contrastive metric, info NCE works much better in all the cases, although it's very, very close, but then it's smooth L1 is still performing much better than that. Percent similarity is better than info NCE, so that's again surprising to me. So another experiment that they did is by using different, okay, yeah, that is, okay, yeah. So another thing that they did is by just using a 3D point encoder and then using the same thing for reconstruction loss as well as for the contrastive loss. You can see that vanilla multitask learning is actually not performing that well, but by using the two tower network, which is the recon method, they are actually performing much better than any other modeling part. So I think the main part which they mentioned is because of the one thing that all the other models they left out is that the gradient should not be flowing. That since the gradient should not be flowing from the contrastive loss towards the contrastive model towards the reconstruction model. So because of which it actually reduces your accuracy. So they give all the credit to this to stop gradient method. One limitation for this problem or for this architecture is the prompting approach. So in the previous architecture which I showed, on the right hand side you have the text input, which will be mentioning like what type of input do you want to have in this model. So in this case, they have given an example of a point cloud of an airplane that is coming from your clip model. But imagine, so in the code that they have provided, you guys are not able to see that. So the code that they have provided, they have a template for the prompt itself, which is like it's mentioned a point cloud model of a 3D rendering model or something like that. But then what I found out, even if you try to run that, you will not have a good generalization of the prompt in order to generate that particular image. And this I feel like is a limitation in this case. Since they have just hard coded the prompts and to make a template. The second limitation of this model is the architecture itself. From looking at the image, from looking at like what they're trying to do, it's like a very complex part that they like what they're trying to do just for a simple downstream task, which I feel it can be modified in a much better way, rather than just doing everything in this one model. So even though it's a teacher student knowledge distillation model, the part which actually is important is like you can, I mean, even if you have like two different models, you can actually try to do something much better than this, because you have so many blocks.
Have you seen the list here?
So LSTM is okay, but this is very complex. You're using clip for this text input, like that's anyway a very, very huge model. And then you're using VIT, and then you're also using MAE decoder. So there are a lot of things which are just
Replace the clip with ChatGPT API.
making one small become much bigger one. So yeah, this is the overall explanation of the paper. So they just proposed, so as a summary, they propose a contrast with reconstruct model that has the metrics of both generative mass modeling as well as the contrastive modeling, which they are using to scale the multimodality data to facilitate stronger 3D representation learning. So yeah, and that's all. Any questions?
Thank you, Mrinal. Yeah, with your critique, I still didn't get, okay, smooth L1, maybe worth trying, but smooth L1 as a loss for contrastive, like instead of this information consensus.
That's what my question was, like, why is smooth L1? How smooth is one actually working when you have a better, like better metric, which is influency?
Well, like if it's too negative, it's high. If it's too positive, it's high, and then it's just smooth,
Smooth out.
near the zero, so the gradients can flow. Because I mean, L1 is not differentialized.
But still, I mean, I figured like if you have like influency and you have like one positive sample in this case, and you just put like all the others as negative samples, it should still work in a much better sense. Smooth L1, I still don't figure out, like, I don't know how it's working much better than the actual contrastive metrics. Like they did not, so they did mention Infomax as well, but they did not try that metric, or at least they didn't show it in the ablation study.
Yeah, that's interesting. And did it perform well at least? You said it's.
Yeah, it's performing well in all these tasks. So all the experiments that they did. So for object recognition, like 3D synthetic object recognition, as well as for zero shot recognition. So it's actually performing much better in all these data sets and from all the other models that are there in like currently which has been published.
Mhm.
So that's one thing. But yeah, I mean, I generally, I thought of searching for more papers which are related to 3D reconstruction, but since this is like the latest one, ICLR 2023, I didn't see anything which is better than this in this case.
That's interesting. Although, yeah, the model, yes, it looks complicated, but maybe it's just a figure.
When they do the masking part, how do they determine the mask tokens? Are they like just randomly chosen or are they learned somehow?
The masking of,
Yeah, I guess for the masks that are passed into the MAE. I don't remember that.
that mask is actually, but they don't do the random masking in this case because that doesn't make, I don't think that could make sense, but I guess the masking in this case, it's just a token. Well, even I'm not sure, like if they do some random one or not, let me check that. Yeah, they haven't really mentioned anything about the masking thing.
Well, again, too bad Alex is not here again. But a comment about decoder. Usually decoder is very costly. Like your representation, you quickly compress it to a small vector and you can work with it. But then you have to decode into, especially think about 3D brain images and things like that. You have to decode into that space and make it correct, and too many parameters in the output layer of the decoder. And that was their Alex's and Devin's deep Infomax kind of thing, that you replace the decoder by operating in the representation space directly. You probably cannot do reconstruction, but maybe you could, I don't know, somehow reconstruction in the representation space. Not sure what that would mean. And yeah. And I thought when I saw this slope gradient, I thought you were looking at this paper because of your trouble.
Yeah, I was.
I was. Stuff, like how to flow the gradient, and student to teacher, and all of that. That's interesting. Okay, if we don't have any more questions, maybe because Mrinal is talking so fast. We're done for today, I guess. Let me just, since we got time, let me quickly check what's next. Okay, Nina, supposed to be next self-training with noisy student improves ImageNet classification. Yeah, that's also continuation of self-training, contrastive training. We'll see. Nina is sick today, so hopefully by next week she'll be back and places. Okay, thanks everyone. We're finishing our recording and then stopping the meeting because I can't find the stop recording button. So my side.
Oh.
Yeah.